So section 12.3, still looking at surface areas, but today we're looking at surface area of pyramids and cones, things that come to a point basically. So pyramid, a polyhedron with a polygon for the base, and the lateral faces are composed of triangles with a common vertex. So the base can be any polygon shape, can be a square, triangle, hexagon, pentagon, so forth and so on, but all of the lateral faces will always be triangles. Lateral edge is going to be the intersection of two lateral faces, so where two of those triangles come together is going to be a lateral edge. The base edge is the intersection of the base and a lateral face, so where one of the triangles and the base come together is a base edge. The height or altitude is going to be the perpendicular distance between the base and the vertex. So from the vertex to the base at a perpendicular intersection or right angle would be the height or altitude. If it's a regular pyramid, it's going to have a regular polygon for the base, and the height's going to meet the base at its center. So where this height hits right here is going to be the very center of the polygon. And slant height is going to be the altitude of any lateral face. Since the lateral faces are triangles, the slant height is basically just the height of one of the triangles that makes up the lateral faces. All right. So we've got a wooden jewelry box in the shape of a regular pyramid. Use the diagram of the box to find the area of each lateral face. So the lateral faces are triangles. So in order to find the area of the lateral face, we use the area formula for a triangle, which is 1/2 the base times the height. And so when we look at one of these lateral faces, what we recognize as the slant height for the pyramid, since the slant height is the altitude of a lateral face, that means that that slant height is actually the height of the triangle that we need to find the area of. And then the base is just the length of the sides, which tells us each side is 10 centimeters. So first thing we need to do, or what we need to do to be able to find the area, is figure out what the slant height is, because they didn't give us a value for the slant height. They did give us a value for the height, and we know that one side is 10 centimeters. And so since this is a regular pyramid, we know that that height segment is going to be hitting in the very center of the base. So the distance from that point to the side is going to be 1/2 the length of the side, so 1/2 of S. So if we look at just that triangle, because we've created a triangle there with the slant height, the height, and 1/2 the distance to the of the side, and it's a right triangle. All right, 12, 5 is going to be 1/2 of 10 for that base side there. Now if we look at it, we have a right triangle. We're trying to find that side, which is the slant height. So in order to find that slant height, it's actually the hypotenuse of a right triangle. They've given us two sides of the right triangle, so we can use Pythagorean's theorem to find the third side. All right, c squared equals a squared plus b squared. And so our c is the slant height, which the symbol we use for slant height is a lowercase l, usually a cursive version of lowercase l if possible. So lowercase l squared equals 12 squared plus 5 squared. So that's going to be 144 plus 25 L squared equals 169. Take the square root. And our slant height is going to be 13. So now we know what the slant height is for the triangle. That is actually just the height for the triangle. So now we can plug into the formula. A equals 1/2. The base is 10. And the height is 13. So 1/2 of 10 is 5. 5 times 13 is going to be 65, and the units are centimeters, so centimeters squared. So in theorem 12.4, surface area of a regular pyramid. Surface area S of a regular pyramid is S equals capital B plus 1/2 of PL. So B and P, same thing as yesterday. Capital B is the area of the base. Capital P is the perimeter of the base. And the L, like we discussed up here, is the slant height. So area of the base plus 1/2 of the perimeter times the slant height. So using that formula, come down here and find the surface area of the regular pyramid shown. So surface area is area of the base plus 1/2 the perimeter times the slant height. Watch the parts that are easy to come up with. The slant height, they gave that to us. That's 9 feet. Perimeter is pretty easy to figure out. It's a regular hexagon base. So shows that each side is 4 feet. So 6 times 4 will be 24 feet. And then the tricky one, capital B, or area of the base. In order to find that, we've got to use the formula for area of a hexagon, which for most of you probably don't have that one memorized in your head, like you might have area of a square or a triangle. So formula for a hexagon, or really any, you use this formula for any polygon, a square, any regular polygon, a square, a hexagon, pentagon, octagon, is 1/2 of lowercase a times p. Everybody knows that p is the perimeter, but the a is something called the apothem, which an apothem is like the equivalent of a radius in a circle. So, or the polygon's equivalent of a radius. So it's the distance from the center of a polygon to a side. So kind of like a radius is the distance from the center to the circumference of a circle. So when I look at this hexagonal prism, we've got the center point here, which, and if we go from there to each vertex, it makes a triangle. The apothem is this line right here, going from the center to the side, intersecting it at a right angle, because the shortest distance from a point to a segment is the perpendicular distance. Right? So this triangle here, I've kind of made a representation of the base over here as a hexagon. If we connect all the vertices to the center, we get a whole bunch of triangles, right? And if we look at these triangles, going all the way around would be a circle, so that would be how many degrees? 360 degrees. So it's 6 sides. So 360 divided by 6 will be 60. So every one of these angles here in the center is going to be 60 degrees. Now, so when we look at this figure here, we're trying to figure out the apothem, which the apothem is going from the center to the side, intersecting at a right angle. And so, since these are all isosceles triangles, the altitude is actually going to cut the sides in half, and it's also going to cut the angle in half. So that gives me one triangle. Where if that 60 cuts in half, then that leaves me with a 30-degree angle there. Now this one's a right angle. Now that one's 60. And when we look at the picture, each side was 4, so that apothem is cutting each side in half. So each side of this line is 2. So for that triangle, that side is 2. Which when we look at that triangle, that is a 30, 60, 90 special right triangle, right? So they gave us the short leg, and we're trying to find the apothem, which is the long leg. And the relationship that we should remember for 30, 60, 90 triangles is that the long leg is the square root of 3 times the short leg. So it's going to give this one 2 square roots of 3. So A up here is 2 square roots of 3. So now that we know that, we can go ahead and find the area of the base. So area of the base is going to be 1/2 of the apothem, which we just figured out is 2 square roots of 3, times the perimeter, which we know is 24. So 1/2 of 2 square roots of 3 is just going to be the square root of 3 times 24. 24 square roots of 3 feet squared. So now we have all the parts to plug into the surface area formula. We've got the area of the base, the perimeter, and the slant height. So surface area is going to be area of the base, which is 24 square roots of 3, plus 1/2 of the perimeter, which is 24, times the slant height, which is 9. So 24 square roots of 3 plus 1/2 times 24 will be 12 times 9, 108. So 24 squared is 3 plus 108 feet squared would be the exact answer. Or if we went ahead and multiplied that out and rounded it, it's going to be approximately 149.6 feet squared. So this example is one of the more difficult examples of a surface area for a pyramid, just because we had a hexagon for the base. We have a simpler figure like a square, then this goes real fast. But really, anytime you have a hexagon, it's going to be a 30, 60, 90 triangle that you're finding the apothem. So it'll be the square root of 3 times whatever half of the side is. Alright, so cones, or a circular cone, has a circular base and a vertex that's not in the same plane as the base. So you got a circle and then some vertex that is above that circle somewhere. A right cone is a cone in which the height meets the base at its center, just like a right pyramid. The height hits the center of the circle. Lateral surface of a cone consists of all segments that connect the vertex with the points on the base edge. So basically what that's saying is the lateral surface is all the segments that would join the vertex to the circumference of the circle. So if you draw enough segments in there, eventually you have a solid surface. Right? And so we've got a slant height on a cone, the base is a circle, the height is going to hit the circle in the very center if it's a right cone. And if we flatten it out into a net, it's going to look something like this. We're going to have the circle for the base, and then all the lateral surfaces are going to look like Pac-Man. Alright, so theorem 12.5, surface area of a right cone. Surface area S of a right cone is S equals pi r squared plus pi r L. Right. So, once again, things with a circle in them are going to be simpler for us to do because we always use the same formulas. We don't have to come up with what's the area formula for the base because every circle, the area is pi r squared. So, we find the surface area of the right cone shown. We only have to know two things in order to find the surface area of a cone. We have to know the radius and the slant height. And the radius here is 5 inches. The slant height, or L, is 8 inches. So if we plug that into the surface area formula, it'll be pi times 5 squared plus pi times 5 times slant height 8. That's going to be 25 pi plus 40 pi. Combine those together and we get 65 pi inches squared. Or if we multiplied by the pi and rounded it, it would be approximately 204.2 inches squared. So that's surface area of cones and pyramids.